Truncated Taylor series to approximate functions. Firstly, what truncated means is, truncate means to cut off. So what we're going to do is we're going to cut off the Taylor series to a finite number of terms, and we're going to use that to approximate functions. So we can have an infinite number of terms for Taylor series or power series, and that's really nice because if it converges, it will converge to an exact value that we want. Now, this is a really nice, elegant use of math, but we cannot actually do this in practicality because we cannot deal with an infinite number of terms. So we have to approximate. So at some point, when we're dealing with Taylor series, we're going to have to cut it off and say that this is as far as we can go, and we're going to use this polynomial to estimate what we're trying to calculate. So just a reminder here, I've got drawn again the sine x example. So we have in red the sine x function, and we can see that as we increase the number of terms of this polynomial, so we have n equals 1, we have n equals 3 here, and as we add on, we go from a linear function, which we have in blue, the cubic function, which has been drawn in black, the fifth degree function, which has been drawn in green. And you can see that as we increase the number of the degree of the function that we're using, or the number of terms of the Taylor expansion, we're going to get better and better and better fits. Okay, if close to zero, it's going to be always going to be a really good fit. But even as we go further away from the center, the higher degree polynomials are still going to be better, are going to become better and better fits. So if we take a look here at the first degree polynomial, if we're approximating pi, okay, it's going to be way up there. But if we use a third degree, it's a little bit better. And the fifth degree is even better. And if we use a seventh degree, it will get even better. And we can make that same analogy for any terms for where this series converges. And this series, if we do a ratio test, we can show that it converges for all real numbers. So as long as we use enough terms, we can calculate as far from the center as we want to go. Okay, because eventually the polynomial will match that curve better and better and better. So again, this is a big idea then, is that we can increase our accuracy of approximation by increasing the number of terms. Now, this is something a computer can very easily do, and we use computers with these series to calculate values to whatever degree of accuracy we need. But the question is, what if we want to quantify the bounds of error? What if we want to know how much error is possible? Within what degree of error can we expect this function to be accurate to? That is what we're going to look at next. So we're going to look at this in part 2.